Good afternoon, everyone. Welcome back for the afternoon session for the first day of the Charm++ workshop. So it's my pleasure to introduce Robert Wisniewski, who is currently the Chief Software Architect for Extreme Scale Computing at Intel and a Senior Principal Engineer there. Previously, he spent 15 years at IBM working on the Blue Gene research team, where he was also, excuse me, he was also a Chief Software Architect on that project, leading up to the current, top whatever Blue Gene Q architecture that's in widespread deployment. So today, Dr. Wisniewski will be talking about HPC system software vision for exascale computing and beyond. Thank you.
Hello? Oh, there we go. Okay, great. Okay, so I'm from Intel. So I thought I would spend a little bit of time for the folks who haven't been in this community giving my view from a software perspective, that is, what exascale is, what it means. I'll talk a little bit about the hardware trends because after all, we software architects and engineers and developers are affected by the directions that hardware is likely to be going. And then I'm gonna talk a little bit about that this is a continuum. We shouldn't be focused so much on exascale. I'll spend the majority of the time talking about software components. And in that, I have threw in a couple extra slides from previous talks that I've given about runtimes, given the distribution of folks in this room. I'm also try to finish a little bit early so that we have time for questions. But please, as I'm going through, feel free to ask me questions. So, where are we? What is exascale? Today, if you take a look at what the top machine is, it's roughly 50 petaflops, right? So that's a 20th of the way to exascale. So that machine is about 125 racks. If you've been in a reasonably large computer room, 125 racks is not huge, but it's not small. If you take a look at where the bookends are on this, the K computer, which was number one in the world, a couple top 500 lists ago, was 800 racks. So that fills a pretty large data center. It probably overfills most data centers. They had to build a special room for it. On the other side of things, Sequoia, which was number one a bit ago, that was the Blue Gene Q machine, is about 100 racks. So we're talking about pretty large machines. I'm going to come back to the actual definitions of exascale. Let's first walk through some hardware trends that are going on. Certainly, a lot of folks have heard about NVRAM, different technologies, whether it's phase change memory, whether it's just flash, whether it's MEM resistors. I think very fortunately, some of these technologies really are going to be coming into fruition in very near term, next generation and next generation. And the reason I think this is so important is because if you take a look at how we do I/O today on large HPC machines, oversimplifying a little bit, the lifetime of a bit, it starts off on spinning disk. It's brought in through a potentially cumbersome I/O system. It's brought into the chip, and then through the cache system. Eventually, it goes into register. A little bit of computation is done on that, and it goes all the way back out. And for folks who are in the I/O space, I think we all recognize that this model just isn't going to extend, whether it's just doing checkpointing, whether it's just writing out data sets, or whether it's really doing the full input-output. We would have been broken in the coming generations if we had to continue going with this. But NVRAM technologies are coming along, and they're going to substantially impact how we do software. So that's one trend that I think folks are aware of. I will talk a little bit later on how we can leverage this, but it is going to help us. A second trend, as everybody knows, is the number of cores are increasing substantially. Clearly, the biggest change from yesterday's generation of supercomputers to where we're going to be in exascale is the intra-node architectures are what's changing. And there's two swim lanes, so to speak, in terms of where the design points are. One of them is that we'll just continue leveraging the increasing amount of silicon and putting more and more cores on them. And whether they're cores or heterogeneous cores or just lots of small cores or maybe lots of bigger cores or whatever, one potential swim lane is that there's going to be a lot of cores. The other approach is that we'll take some type of commodity building block that is being delivered, say, in cell phones or in tablets, that will become very cheap because we as an industry will manufacture billions of these, but we will, from an HPC perspective, leverage them and leverage what's going on in the commodity space and figure out how to put them together. Regardless of which approach you take, just to get to exascale, one of the things that you'll note is that there's going to be a lot of these, right? So this is kind of roughly a straight line computation based on where we are and expected technology increases. But we're talking about lots of cores, right? Order roughly 100 million by the time we get to exascale. So let's come back to what is exascale. Mathematically, it's 10 to the 18th operations per second, and I'm explicitly trying not to say exaflop, right? There's been a move in the HPC community away from just measuring computation by LINPACK, which is just a flop number, towards trying to measure it by useful work in real applications that are going on. Okay. From a software perspective, I really see the biggest three challenges are power, scalability, and reliability. And I'm going to focus a lot of the thoughts in the rest of this talk on what we can do to address them. Straight line projections get us to 350 megawatts. I personally believe, I think there's some smart things we can do in software on power. We saw a good talk earlier today. But I fear the bulk of this burden is going to have to be done by the hardware architects. We're not going to get 5x improvement by doing something smart in software. But there are other areas where we have real serious challenges in software that we are going to have to overcome. Like I mentioned, we're talking roughly 100 million computing threads. At that size, if you, and I've given talks at reliability studies and reliability workshops, and sometimes I'll ask, how long does your laptop stay up? And the folks who are running Windows jokingly say maybe a day. If you're running a Linux machine at home or in your computing center, and you say it stays up for a year, people think you're doing pretty good. But if you back project out and you say, I want my supercomputer to stay up for roughly a week, somewhere between a day and a week, and you back project out how long at this many computing threads, making some assumptions, you're roughly talking about each Linux or each OS instance needing to stay up for 50,000 years. So that's a when you calculate it out that way, that's a pretty big statement in terms of how we're going to be reliable. And then like I also mentioned, we got this other challenge that from a software perspective, we got this hardware technology that is coming along, that thank goodness is coming along, that we are going to be able to leverage. But the question is, how should we leverage that, and what type of models can we do to do that? So I've been involved in exascale workshops now for at least, more than 5 years. The DOE started them probably 6 or 7 years ago. And if I characterize some of the thinking that started 6 and 7 years ago when we first started looking at exascale, there was a sense that this is a very challenging space. It is. But there was also a sense that all the current models that we had, whether it was the current compilers or the current operating systems or runtimes or languages, they were all going to need to change. And so I kind of characterized that. This is supposed to be Chicken Little. Sorry, the Intel lawyers got a hold of Chicken Little, but this is Chicken Little. And for the Americans in the audience, there's this sort of fable that Chicken Little was out in the field, right, running around, and something fell and hit him on the head. It was actually an acorn, but he thought the sky was falling. So there's this expression that the sky is falling. And if I were to characterize when we first, as a software community, started looking at exascale and how we were going to get there, there was this real sense that it was going to be this extremely hard problem. It is, but that none of the current technologies we had were going to get us there. Some other, the other camp, and I was kind of hard in this other camp for a while, started advocating, well, we have a lot of good technology now. Let's just figure out how to evolve this going forward. So, there was this other camp that was advocating, taking what we have, kind of an evolutionary approach. So if I were to characterize these two disparate approaches, we can either say, to be able to get to exascale, do you need a revolutionary approach, or do you need an evolutionary approach? And if this was a panel, I would stop and take everyone's opinions, but think which one, from your perspective, you think we need to get there. And what I'll claim is that it can't be revolutionary only. if I, as a vendor, said to all of our customers who probably have invested more than $1 trillion in the IA ecosystem out there across compilers and ISV codes, et cetera, you know, everything you've done over the last 2 decades, throw it out. We have a better idea. We're going to start over. Whoops, sorry. You know, clearly I would be shocked probably, right? That just isn't a very viable perspective. So it can't be only revolutionary, but I'll claim also that there's a lot of serious challenges to getting to Exascale. I named some of them, and I'm going to come back and tell you how I think we need to address them. But we're not going to get there evolutionary only, right? You know, monkeys never learned to program computers, although some of the codes we look at may may be explained by that. So what I really what is this? Okay, so sorry, I don't know why this is, it's a little slow. So what I really claim is what we need to do, and this is a message that I've been giving internally to a lot of the Intel teams, and I've delivered a few external talks on this. What I claim that we as system software folks need to be able to do is there are real serious challenges, and we do need a lot of revolution to figure out how to get us there. So what I claim we need to do is we need to figure out a way to support the existing computational models, right? Be it MPI, be it C++ or C or Fortran, be it some of the runtimes we built up. We need to be able to support those, and the key word here is simultaneously. That's why I got it bold and underlined, because we need to be able to simultaneously do that while allowing portions of the application to be reprogrammed to some of these revolutionary models to address the challenges that we're seeing coming up to Exascale. So just to summarize, we need to be able to support, you know, at the same time, both revolutionary and evolutionary. And the biggest challenges are, right, we have to be able to scale. The system software has to be resilient. And you know, I have the last book, because power is important. So I say be power aware. I don't say that we have to solve the whole power challenge. Where is this? Somewhere I lost. This is really weird. Oh, I lost a slide in here. Oh, well. Let me also, sorry, I'm going to go back a little bit. I was wondering where this slide was coming from. So let me make another observation. We keep talking about Exascale, right, as if it's the end, right? Exascale is not the end. You know, one of the things that I'd like to think is many of us, in fact, especially in this audience, a lot of us, are going to be working in computer science well after Exascale. So I made this observation, and if you look at peta exa zeta, I got PEZ, right? So I'd like everyone to think that Exascale is not the end goal. We should be thinking about system software as a framework to get us to Exascale, yes. But we shouldn't be designing methodologies and technologies that are going to fall off the cliff. And somewhere else there is a cliff here with Exascale. I don't know what this thing is slow. Oh, well, it doesn't matter. Okay, anyway, so we really should be, so, you know, that's the other message, is that think about the challenges of getting to Exascale, but you know, make sure your thing works at 10 Exascale too, or at least the methodologies you're putting in place. So how are we going to do this? So I mentioned this notion that we have to do things simultaneously, which sounds kind of scary at first when you really start thinking about this. So let me give you an example from a communication perspective, how we might achieve this. And see, Sanjay even got, look at this, target it right, there we go. And I showed this slide at Celishan. I don't know if you were carefully paying attention, but so what I would claim is, you know, 10 years ago or 5 years ago, some N years ago, applications really just used MPI. And you know, I don't mean to claim that OpenMP is revolutionary. I know Charm++ is. But you know, what I claim is that an application has to be able to, at the same time, have the bulk of their code which uses MPI, and be able to call ER. You can think of different acronyms for it, but Exascale runtime, right? Whatever that magic runtime is that everybody, you know, has told me we need. We have to be able to simultaneously call those. So when I say that, you know, in some sense, we've already figured out how to, you know, exist with MPI and OpenMP, coexist. Although, you know, from some perspective, OpenMP really doesn't compose too well with some of the other runtimes. So what I claim is one of the solutions we need to do from a communication and runtime perspective. And I know Vivek's working on OCR, so I'm sure if this slide sings to him. But we need to be able to figure out how to have this common runtime base so that an application isn't restricted to just a single evolutionary approach, I'll call it, that we can allow these new revolutionary ideas to be called simultaneously and not require, and not just have ER be across this whole thing. Because if I were to draw you two graphs, one with the application with MPI across the whole thing, and I said, or you can have the application with the Exascale runtime across everything, that doesn't sell too well, right? I don't know if Robert's still, yes, Robert is standing back there. Right? That doesn't sell too well to the applications. We need some model like this. But when I cast it like this, and I say, you need to be able to call MPI plus OpenMP or MPI plus something else, people kind of nod, yeah, I can see how I can do that. But the challenge, the charge, right, to the Charm++ team is you guys, and I'm going to come back to this a little bit, but you guys want to fit in here. I mean, I know you'd love to take over the whole world, and that probably would be great. But to get there, right, you need to sort of coexist. So another space for some of the folks who know me, my background is in kernels, operating systems, and execution environments. So, how are we going to get there, do the same type of thing, allow revolution while still supporting existing computational models? In the execution space, the common API is Linux, right? If I were to ask you what you wanted from the OS, some people kind of just say Linux. You actually don't want Linux, you want a Linux API. You don't really care what's running underneath if I just provide you Linux. So years ago, I worked on this project called K42, and the notion was, this was, 15 years ago, when the community was still voting whether we were going distributed or shared memory, right? So IBM and SGI were building larger and larger shared memory machines. K42 was this initiative that said, how should we design an OS from the ground up for if machines really go large, scalable shared memory? From this talk's perspective, though, the important part is we said, well, you know what? In this environment, there's going to be some cases where we need to call revolutionary new ways of doing things. And so we allowed in K42 the ability to call native or reach around Linux and call native interfaces while using Linux for everything else. The end point of where a series of research really is going is what you really want to do is you want to have your application up here, and for the calls that matter for extreme scale, and so EX is extreme scale OS. For the calls that matter, you want to be able to call your extreme scale OS, but you don't want to encumber whatever the next generation of operating systems are, implementing all of the Linux API. For all the rest of this stuff that you don't really care about the performance, you want Linux there. So we have this initiative called MOS, which stands for multi-OS. And what we're saying is compute nodes now, just like in past, BlueJean as well as Cray, have offloaded some OS functionality, primarily I/O, from the compute node off to I/O nodes. One of the observations we've made with MOS is the fact that we got a lot of cores now on the compute node, right? We all know that Knights is already 60 cores and growing, and even the Xeon line itself is growing to a large number of cores. So the observation we're making is we want to introduce another level of hierarchy, so to speak, and take a series of those cores and run a lightweight, nimble OS that can support the revolutionary runtimes, right? In a very efficient way. Work, partner with OCR, or be able to provide really neat things, the Charm++ that you guys would say, hey, if only the OS would give me this. Well, we can do that in a lightweight kernel, but the plan is to also run Linux there and to still have it be available in the case that the application has made some call that we chose not to support in the lightweight kernel. The lightweight kernel can call over to Linux. So in that sense, we're supporting the existing computational model, which is a Linux API, but yet we're still allowing the ability to call whatever new HPC call we need. Yeah? So the question was, why not just implement these, the lightweight calls you want to make into Linux? So one example is memory management. Memory management inside of Linux has its fingers kind of everywhere. And if you've looked at over the last 10, 12 years, Linux has piece by piece started providing large page support, right? So this is just one example of this. Well, 10 or 12 years ago, I had, a half of one person on the BlueJean team, which implemented large page support, did it transparently, and it just worked for the applications. The reason it could do that, I believe, there's good developers on both sides, but the reason it could do that, it was fairly targeted. Linux, on the other hand, really has to support this generality. It has to work for all people, right? So one of the things that we can do in the lightweight kernel is we can make, from a Linux perspective, unfair simplifying assumptions that you couldn't do in Linux, and we can put in really targeted things, and we don't have to be encumbered by providing this just generality of things. So if you, there may be a model of trying to like embed little servlets in Linux, but in some spaces, Linux is designed to be able to do that, like a scheduler you might be able to jam in, but in some other spaces, like memory management, you can't. Yeah, good question, though. Thanks. Okay, so this is from an from an execution perspective. So I talked a bit about the I/O, right? So what are some of our thinking in terms of how we're going to leverage the I/O? Right now, as I mentioned, how do you write out I/O? You linearize it through a POSIX or file system interface, right? So in the future, there's going to be this NVRAM that is packaged, at least logically packaged, with each of the compute cores. And some of the technologies don't have the terrible wear-out properties that your flash on your camera does, right? So it will be able to be used like memory. You'll be able to write to this NVRAM via a load store interface, and it will last for the 5 years or the lifetime of your supercomputer. So in essence, what we're going to see is a model where your notion of the application's notion of memory is a combination of standard DRAM as well as this NVRAM. So in that model, it no longer, I don't want to say makes sense, that's sort of a poor way of casting it, but wouldn't it be nice if once we have moved to this model, if instead of saying, now I want to make this data structure, be it some classical, array or classical HPC array, or if it's one of these new analytic data structures, graph nodes or trees or whatever, wouldn't it be very advantageous if rather than having to now call some I/O structure, which is going to linearize it through POSIX and turn it into a permanent storage thing, if you could just call an OS call that said, make this data structure permanent. And I don't know, conceptually, there's no reason why you can't do this. It after all, is already sitting in NVRAM. So these are some of the ideas that we're exploring to leverage the I/O. Now, go ahead, please. That's a good question. So if you're familiar with some of the Deos work that Eric Barton is doing in Fast Forward, he's exploring some of these ideas. There's two components of it. There's two components of this. There's treating it as, there's treating the data in the NVRAM as disk, and then there's also making it durable. And there's sort of two aspects to that. But it would look just, it could look like, sorry, not it will, but it could look just like memory, right? That is one model. Or you could embed it into the I/O thing. I'm actually really pushing, if you want to think revolutionary, I'm really pushing longer terms out and really having it look just like load store memory and then just flipping a bit and saying I want this permanent. But I don't have to implement it, so that's that's maybe is an oversimplification. What did I do? Oh, oops, jeepers. Okay, so all right. So let me take 2 slides now and talk about some ideas for runtimes, and then I'll conclude and take a few questions. So one of the areas where I really believe that software can help is in the area of reliability. Right? There's 2 different axes we can look on this, and afterwards I'd be happy to take questions about sort of system level reliability. But a lot of work, I know I've seen a lot of the wonderful Charm++ papers have talked about reliability. And one of the reasons why that I believe Charm++ or CNC type architectures allow us to explore this is, here's a simple, a simplistic, overly simplified, I should say, notion of how we might do reliability. Just imagine that that you've divided work up into tasks rather than kind of these directive things, right? Rather than a PC flowing. So you now have a task of work that needs to be done, and as input to that, you have what data it needs, right? So I'm not going to a fully data flow model, but you have what you have what input it needs, and you also know what other tasks have to have completed prior to this task coming, and now you throw them all into a bag, right? You throw them all into a bag, and And now you have a runtime that can schedule these tasks. Well, if a particular core on a node goes down, oh, one more assumption. We're going to design hardware in the future that allows really cheap threading. I don't know whether that's true or not, but I'm going to push the hardware teams to do that because, as Vic and I were talking about over lunch, I think there's a lot of good reasons to do that, whether it's for OpenMP that we know is going to be needed or some of these new models. So assume that you have hardware that supports really cheap threading and really cheap switching between threading and coordination. So, and you guys will like that for Charm++ too, right, if you had hardware that supported threading. So now you throw these all in, you have a runtime that can very efficiently throw tasks onto cores, and if a core or a piece of memory or logic on a core goes belly up, the runtime can notice this and just move that computation to some other core and continue. And if these tasks were idempotent, right, that didn't actually create memory, or you could run them speculatively, or lots of other interesting notions we see, now we could actually have the runtime giving us some amount of reliability. So let's talk. Oh, boy. OK, so let's talk about some of the areas where I really see runtime, such as Charm++ or CNC or other types of research in runtime being able to help us, to help solve some of these problems that we need to address going forward. So one of them is in resilience. I really see the runtime as a good place that we can start thinking about trying to provide resilience. And I know I've read Charm++ papers in this space as well, but you know, one of the things we need to do is we need to integrate this node-level resilience with system-level resilience. And again, I'm not going to take the time to talk about that here, but afterwards I'd be happy to. Another place which we've talked about is asynchronous behavior, right? Robert, in his keynote at the beginning, indicated the value of doing this, and this is another place where runtimes can really advantageous this. The last or two talks ago, we saw how runtimes can help us out with power. I think this is another area. And facilitate fine-grained threading. This is obviously something you guys already do, but there's a couple advantages that that will bring us. The question that we need to do is, when we come up with any of these solutions in the runtime space, just in terms of being pragmatic, this is my view, not an academic's view. I recognize that, right? So we have to somehow marry these two solutions. But we need to understand how that solution makes a scientific contribution. That is something that you guys definitely, from an academic perspective, really focus on. We have to sort of, as we start bridging the gap, we have to talk about how it really helps applications across the spectrum, not just a given application, right? But if we really want to change how runtimes are used, it has to be generally applicable. And then finally, we have to figure out how it fits into the software system stack. And I say fits in or valuable to the current because it's unlikely, at least if we really want to get these things deployed, that we can wholesale change it. So why are we doing all this work? One of the things that really excites me about high-end HPC is the fact that we get to help create new science, right? And new science really is in some sense, it's changing. As HPC has become more powerful, we're really starting to be able to get into some of the biological areas. So it's the standard things that we've done, being able to move those to the next level, being able to influence industry. It's the new areas that we're starting to explore, being able to discover new biological features rather than just the simulations that we've in the past done. So, whenever I think about my role as a system software person and the roles these machines play, the interaction with the applications have to be center front in our mind. So, just to finish then, the way I believe as a path forward, and it doesn't mean that revolution isn't important. In fact, it's front and center in this strategy. We have to think revolutionary thoughts. But what I argue is that we have to, if we're going to get these accepted and adopted, and applications as a whole, not just one or 2 point examples are going to pick them up, we have to figure out a way to fit these revolutionary ideas into the system software stack simultaneously while still allowing the current existing models to take place. So thanks, and I'd be happy to take questions.
One sec.
It seems to me that reliability over the last forever in computing terms. The computers since the beginning we have not really done much at the software level providing reliability. We have the von Neumann model, and that's what the application programmer gets. And if we're serious about reliability, we will not be using programming languages like C, and we will have hardware that will where it will refuse to execute data. There has to be a authorized something or other that says this is data. And we will also have hardware support for the idea of having a descriptor or regions, so you cannot have an I/O going from the network and just stringing on past the buffer and pulling out people's passwords.
Yeah. So I think,
and that's a hardware thing that ought to be there.
So you put your finger on, I think, one of the key issues in this space that I really didn't touch on. So I work really closely with Al Guerra, who is sort of the father of Blue Gene. He was at IBM. Now we're both at Intel. And when I talk to him about some of the ideas I have for software reliability, he kind of looks at me and says, well, none of this is going to work because of some of the things you said. How do you know if memory has an escape? Okay, so fine. So 10,000 instructions later, you've detected a fault. But what's happened in the meantime? And so my comeback is more or less what you're indicating. This needs to be a partnership with the hardware. We need to figure out a different hardware model. I don't think the hardware has to change that much. So from a software point of view, we have to figure out what the ask is. If we could design a runtime layer that had these properties, what would we need from the hardware to be able to not let things run away, to not allow passwords or whatever to be snooped out? The bigger issue from just from a compute node perspective, really is the fact that it's all shared memory and anybody can trounce over something. But if there were ways of restricting it so that you could keep it to a core, keep it to a process space, or things like that, where you could really limit, right? Where you could argue about, from a software perspective, what you've been able to trash and what you haven't. Now, some of the software capabilities that I glibly described, or overly simplified described, could be effective. But you're right. As the hardware exists today, it's very hard to envision really a bulletproof software-only reliability model. So it needs to be in partnership with hopefully small amounts of hardware. It's a good observation. Sanjay.
So about what you said earlier about interoperability, you called it something else, coexistence in the stack and so on. I agree 100%. I think the only way, you're not going to one day ask the whole world to switch from the old way of doing things to the new way of doing things. And so so we, for example, in Jam++ interoperates with MPI. You can have modules in MPI, you can working together with modules in Jam++. Got recently refurbished some, so we worked with some application. For example, in Chambo, now there is a module, a sorting module that's a Jam++ based module. So I think I agree with you completely, that is essential, and I want to tell you that we do it.
Great. Sounds good. Robert?
Most of the resilience you spoke about were I guess, about detected errors, reported errors somehow. So it seems that one of the scary things at Exascale is really the silent errors, floating point errors especially maybe. So have you got anything to say about that? And I guess also on the resilience front, you were implying that maybe Exascale, there are new challenges on the OS front for resilience. But are we really going to have that many more instances than we have presently at Petascale? Isn't most of the new concurrency coming from intra-node?
So, okay, so two separate questions there. So on the silent errors, this comes more to my thinking on system resilience. So I've talked to lots of application folks, and this is half a chicken and egg thing. So a lot of forward-thinking application folks have indicated if the system software and or hardware would just help them and tell them about errors, some of the errors they feel that they could handle. So my approach to this going forward is I don't think any of us in the room, but if you do, come and talk to me afterwards, know what the right model is. So my approach, what I would really like to do is take a few applications, maybe a handful, maybe 10, and come up with 10 specific errors that in the next generation we could handle. Let's not try to boil the ocean and completely solve the problem. Let's come up with a handful of things and put them into the software stack. We probably won't get them right, But what we will do is we will get experience with how to report the errors, what the applications can really do with them, what the taxonomy of that error reporting needs to be. So, one of the things I'm looking to do as part of some other initiatives we're kicking off is to try to start partnering with applications to see how we could have this, quote, dialogue about errors. The second question about OS instances. So interesting. So I came from a Blue Gene background, right? And I used to kid people there that one of the charges I was gave when I joined the team, whatever it was 10 years ago, was you shan't get in the way of the hardware, performance or reliability-wise. And CNK, which was a very lightweight kernel, I arguably didn't, right? I mean, I'm sure it introduced a few errors, but it was very minuscule. But when you actually do FIT, failure rate analysis for Linux and other system software, that's actually not true. So I would claim we're almost broken today. Forget about getting forward to, it is true going forward to Exascale, we're at whatever, 30 or 40,000 nodes. We're only going to go to 100 or 2,000 nodes, so it's not quite an order of magnitude. But I would claim, if I do my job right as in high-end HPC, as a system software person, you, the application, don't know that I'm there. I've just given you the hardware that you wanted in the manner that you wanted, and I've gotten out of your way. And we're not, by and large. Linux doesn't today. So I think we already, even, if I could redesign current generations, I would work on the fault rate. So yeah, I think we can do better from an OS perspective. Great,
Okay.
Thanks.
Yep. So let's thank our speaker and prepare for the next talk. He's on the website, so his slides are on. So